Matteo has already covered all of the CNT synthesis, so today I'm more focused on it's not spinning, but actually the post treatment of the direct response, the CNT fiber. So the CNT fiber is a collection of the assembly of the CNT aligned to the one axis. So it's it's a very efficient way to transfer the property of the CNT to the properties of the macromaterials. So the CNT fiber could be as strong as the carbon fiber. Also, can be as conductive as the metal, electrically or the thermally. So it could be the next generation of the carbon fiber. Also, so several companies and industry like the CNT fiber aiming for use in various applications. So there's usually two ways to fabricate the CNT fiber. So one is the direct spinning is actually developed in Cambridge by Cambridge. So basically it's a reactor. There's a reactor in some condition. It's based on the salt CVD method, and then in specific condition it forms a sac of the CNT, and then it densifies in water or other liquid, and it directly forms the fiber. So, but it's actually it's very fastly densified. So it's the demerit of the direct spinning is a very poor alignment and poor structure. So actually the property of the CNT fiber is not so good. But the other one is actually wet spinning. So it's Matteo Pasquale, the Rice University developed this method, and then so it's dispersed the CNT powder in the chlorosulfonic acid. Chlorosulfonic acid is very important solvent to disperse without any additives, any disperser. So and then they form some liquid crystalline phase, and then they spin the fiber with very well aligned and a very dense structure. So it's shows very good properties and very good properties. So that's the direct spinning reactor in my lab. So it's now we have some bigger reactor, and it's has somehow better synthesis. It's like 10 years ago, the results in 10 years ago. So with that time actually we can produce very thin CNT fiber. It's like 0.5 tex and 0.05 tex and 0.1 tex. Tex is a gram per kilometer, so it's the linear density. So that's show this actually slide is showing the process of the direct spinning. So if we pass through this CNT sac in the water vessel, so we can directly collect the CNT fiber, and then otherwise actually we remove the water vessel, and then we use just the empty chambers, and then directly spin the CNT sac. Then actually we can make the CNT film at the bottom of the reactor. So there's we actually plotted all it's by 2017, so it's all the properties of the electric spun CNT fiber, but it's really varies. It's fluctuates, so it's not not showing the consistent results. So we think actually that's the reason the electric spun fiber has very poor structure, poor internal structure with a lot of voids. So it's not actually produce really consistent results at that time. So we think about how actually we combine the advantages of the direct spinning and the wet spinning. So as I said, actually the wet spinning at the CNT was completely dispersed in the CSA and then formed the liquid phase. So we think we may use actually CSA as a solvent to densify the directly spun So we use the CSA, we put the direct response fiber in CSA, and it swells quickly. And then actually the CNT, composing CNT fiber can mobile in the immersed, the CNT fiber immersed in the CSA. So we can stretch in the CSA best, and then we move to the fiber into the acetone, like the coagulant, and then we can make a very dense and then the fiber with very packed internal structure. So, but it takes just 60 minutes in the immersion and stretching, so it's very quick process to improve the properties of the CNT fiber. So we performed actually this process, and we really see some difference. It becomes more dense, and it's actually 10% stretch from the original fiber, and its alignment of this fiber is increased a lot. So this really shows some difference in specific strength. So it's doubled, almost doubled from the specific strength of the fiber, and then there's some clear difference of the modular strain curve. So it means meaning it has a very different internal structure. So that time actually it was the best result was specific strength of the densified fiber is about 4.4 Newton per text. So it was among the best in 2019. So now recently it's maybe over the 5 or over the 7 Newton text was reported in the literature. So, but we actually proposed some. It may be possible to do some continuous process, because actually in CS we just spend just 1 minute to stretch the fiber. So we thought actually it may be possible to continuously treat our fiber like this way. So then at that time actually I started with collaborate project with the company called JO. It's a Korean company who produced CNT powder, but actually they want to expand their business to the CNT fiber. So we performing the project, they actually successfully increased the linear density of the fiber. So yeah, so basically, the problem of the direct spinning is it's very fast, but actually it can only produce one strand of the fiber. So in order to increase the productivity, the linear density or spinning rate should be increased. So, but spinning rate it's directly related to the resonance time of the reaction, so it cannot be increased so too high. Then actually the reaction time is reduced, and then the synthesis yield is decreased. So it's a possible way to increase the productivity of the direct response fiber is to increase the linear density. So it successfully increased the linear density is 100 times above, but the strength is decreased, and then the property of the CNT also decreased. So we decided to adopt our CSA densification method to the high linear density fiber. So if you see the difference in the internal structure and the different scale. So in the literature, there's Pascal wrote a lot of literature about the CSA works, and then that's usually the CNT with high GD ratio is dissolved well dissolved in the CSA, but the high density CNT fiber GD ratio of the high linear density CNT fiber is just about 5 or 10. So we actually suspicious actually the CNT fiber, high linear density CNT fiber is working for the CSA densification. But interesting interestingly, it works very well. So the thick, higher linear density CNT fiber can be stretched by 100%. So it's almost twice the stretch, and then surprisingly increase all the properties from the properties of the pristine CNT fiber. So if you see the dramatic change of the diameter of the fiber, also there's some cross-sectional TM images. So we increase the stretching ratio. You can see some cross-section of the CNT, so it becomes more aligned to the axis. So it's very flexible, also electrical conductive, and then most of the work in the literature is performed in the range of the low linear density because it's a high property. So, but in our case, it's the first time to use very high linear density CNT fiber and then increase the properties of the CNT fiber. So finally, so then we actually try to demonstrate it can be performed in a continuous manner. So we developed a very small continuous densification equipment, and then the CSA is very sensitive to the water, so water vapor. So we put this equipment in the glow box, so we can make as compact as possible. So we put the CS base on top, and then there's the acetone base, and then there's some roller. So we change the roller speed. We actually set the different roller speed from the first roller to second roller. We can actually adjust the stretching ratio. So in order to, as a control sample, we also do the similar batch stretch sample, but the best stretch, highest stretch sample is stretching ratio is about 80%. More than 80% is stretched right. But in case of the continuous sample, even though we use the same fiber, so because it's more than 30%, it easily break during the process. So we reduce the stretching ratio to the 30%. We reliably do the process. So some interesting things. So if you see this is the batch process, and this is the continuously process, and then the shape of the fiber is very different. Also, it's more, because it's 80% stretch, it's more compact. And then, but interesting thing is the specific strength and the specific strength and specific conductivity is all the batch continuously densified fiber has the better property than that of the batch process CNT fiber, even though the stretching ratio is small. So we think about why this happens. So if you see all the structure by the SEM, so if you see, obviously the batch process CNT fiber is the better internal structure. So we expected that the batch process CNT fiber has the better properties. But why actually the continuously densified CNT fiber shows better properties? So we also do some cross-sectional TM images. So, and if you are top row the images, so there's a lot of in the batch process, the CNT fiber shows a lot of the CNT cross-section. So it means actually it's better aligned compared to the other samples. But still, then we actually we see the structure of the CNT cross-section in the high magnification. So we observed actually the CNT shape of the CNT is more collapsed in case of the continuously treated CNT fiber. So we just measure some eccentricity is also of the CNTs composed in the CNT fiber. And it turns out the eccentricity is continuously CNT fiber is very high. So yeah, so this is the Chinese group actually published this result in the Science, and then they also use the CSA densification with some PBO, and then also a lot of group is doing the rolling. So we think actually this mechanical rolling plays a critical role. So in our case, due to the configuration of beds, the CSA immersed CNT fiber has some pressure in configuration of the roller. So it looks like, it seems like this pressure flatten the CNT fiber also affects the change the shape of the CNT composing the CNT fiber. It may be the possible reason why actually the properties of the continuously treated CNT fiber is higher than the batch process. So this is this simulation shows with CSA actually CSA actually has to transfer of the load on the CNT and it's more easily lead to the shape change of the CNT in the composing CNT fiber. So there's some showing the properties or our continuously treated CNT fiber show the high tested strength or high linear density. Everything is good. So and then now actually we have some much higher. Yeah, we can synthesize the CNT fiber in much higher productivity. So so we can combining this synthesis method and then some the densification method, so we can closer to the industrialization this process. Okay, here is the summary, and so thank you for your attention.